Giesige here with Westcats. How do we make science fun? I want to tell you. This is what we're going to do. These pictures right here, I'm going to explain them in a fun way. Alright, so we're going to start with the sun. Okay, solar flares, solar surges, coronal mass ejections, and the sun reaches maximum point. And these flares, ejections, solar surges, they expel millions of charged particles, millions of miles per hour out into the solar system. Right? And when we look at these flares, surges, or ejections, we look at them in terms of circular phasing ribbon swirls. Okay? So we have 1, 2, 3, the fourth one we have the point of acceleration. That's where the density and the acceleration point of these charges are. Okay, so we have all these, these solar winds now. Traveling through the solar system, here they come, and all of a sudden now they start to reach Earth. And once these charged particles and these solar winds reach the Earth, they separate, find themselves on the other side, reconnect, and then slingshot themselves back down to lower atmospheres, distributing themselves at Earth's poles. Charged particles get to Earth's atmospheres. All right, we have what we call the transition of magnetic electrical. So within the atmospheres, we have hot, cold, etc. And each one of those atmospheres is different temperature and pressure. So now we have these charged particles coming in, transitioning throughout these different atmospheres, brought to a maximum, and then they transition. The density of the particles and the connection and reconnection of the charged particles can help create the flow between the different phases of the atmospheres. And then once these charged particles get into the lower atmospheres of the Earth, they start to form this swirl, what we see a counterclockwise swirl, transcending into a weather event. Okay? And we're going to look at it, and we're going to look at how the azimuth curve is brought into play here. All right? So the sun's azimuth, the degree strength of radiance at 22.5, 23.5 degrees from the angle of the sun, according to the Earth's tilt, which plays a factor in the strength of radiance that we get. And of course, this angle of azimuth curve that we have here, this is Northern America, the Northern Hemisphere, North America. The azimuth curve that we have here is going to fluctuate depending on the tilt of the Earth. So different seasons, as the Earth is tilted differently, we're going to have different concentrations and different strong points within this azimuth. Okay, different states will be affected differently through the seasons. So we have these atmospheric winds, negatively charged particles that come in from the northwest, okay, up here, and they are brought down by this low pressure system. There's creating this pressure right here. They're trying to float, fighting this thing right here. We have point of resistance. And then we have these positively charged warm winds coming from the south, the southwest, up towards this point here. Okay, we have these two. And little do they know, but they are destined to meet. It is your destiny. Right, so we have these two charged winds coming, and they go over bodies of water. These waters, creeks, rivers, lakes, aquifers, providing ionization. So all these little electrons creeping up here get picked up by these atmospheric winds. Okay, now there's a heightened state here. And these geophysic winds coming in down here along this radiance curve. They meet at this northeast wall within a circular mountain range. They're traveling, and they come to this northeast wall, and we got a second point of resistance, circular second point of resistance. And you got a nice sphere, nice at this mountain, just circular mountain. We call that N raised 711. The anomaly N raised 711. Now we have this inversion coming down here. The pressure system helps bring an inversion, factor of inversion down, and we have this process of induction. So these guys are really pulling on each other, kind of like a giant squid floating in the water. Then we start circulating, okay? These charges, they want to come together. They start to circulate around this mountain range and the pressure system, and before you know it, they got the magnetism quite fully to the ground, and then we have lightning. And these charged particles are going to ground themselves directly towards the highest opposite charge. Alright? And that is what we call the O-axis. It's everything coming together, you know, all these different shapes and forms from all different angles between the water, the atmospheric winds, geophysic winds, the induction, the inversion, the low pressure system, the circular mountain range, all come to this meeting point, this point of acceleration to create lightning. And that's typically how we as Westcats use to monitor. You know, there are other factors involved, but we'll keep it simple.